So with these high-speed racing systems, we are trying to figure out, well, how do you balance this safety where if you crash, you're basically out of the race. But if you're too conservative, you're too slow and you again are out of the race. And assertiveness, right? But we want to figure out how do we generate agents that can dynamically make this balance based on the scenario, based on the context of how you're racing, right? So, and that's an extreme example of how we actually drive in the real world. But by focusing on the extreme, we ensure that the algorithms that we develop and the methods that we develop will actually make even civilian systems much safer. The second is, okay, well, in order to actually have a high performance in these competitions, you have to have a very efficient autonomous race car that's really looking at the electrical, the mechanical, the perception, the planning, the control, the entire stack. And here we'll speak about, well, how do you automatically tune across this entire stack to come up for a particular track the highest performant race car by design, like that, right? So this is combining the software, the hardware, the mechanics, and the racing strategy. And then how do you ensure that this transfers very well to different racetracks along the way? And then obviously, with in autonomous racing, these are extremely expensive vehicles and these are very high stakes games. So you want to make sure that how crash proof is your algorithms, or to put it another way, you want to stress test and build a search engine to search for when this vehicle will crash, under what conditions, how often, and in which parts of the track. And we want to stress test these planning and control algorithms with these interactive adversarial agents, right? And then in team 4, what we look at, and this is a large DARPA project with MIT and Siemens, is on, well, we don't always have to start a new design from scratch. We could mine previous designs, and essentially this research question over here is focused on how do we have AI-based co-designers for model-based design, or how do we combine previous designs to auto-complete new designs with new requirements. So can I, if I'm Boeing, or if I'm Siemens, or if I'm one of these large companies that have been making like diesel engines or turbines for many years, and I want to make a new one or a new drone, for example, can I mine previous designs automatically and synthesize 80% complete designs with 80% probability of success? And how do I come up with these high performance designs, but in an automatic pipeline? This is really using a lot of machine learning to actually come up and generate these designs that exploit previous designs, but explore new design qualities also. And the other theme of this talk today is really on, how can you get involved? Over the years, we've had many students go through our lab, and they're working in many interesting companies, including that YouTube star. I don't take any credit for him. He has more than 8 million subscribers, but he's one of the early people to work on for F110. And then similarly, we have many students involved in different independent study teams. This is from 21. There's other from each semester. I think there's about 18 students in this semester. And then we have many students involved even in this semester on different projects, right? So we'll cover some of these later on if there's some time. So we'll focus more on theme 1, and then I'll focus on opportunities on how you can get involved. Since we're a little bit out of time, I'll skip through some of this stuff in the middle. But let's get started with this, right? So our goal is that, given a new race that we're going to be in, and a set of competitors that we have to race against, which we don't know much about how they're going to race against, how do we generate, a driving policy that is extremely competent and also extremely adaptive to how the other drivers want to race, right? But we want to always make sure that we are safe. We have a certain set of certain robustness, and we are as aggressive as possible, right? When you and me drive on the street, we want to be as safe as possible, and then we want to sort of get to our destination as soon as possible. But when you're racing, you want to be safe enough and then as aggressive as possible, right? So this is based on an ICML paper written by some of my students and called Formula Zero. And essentially, Formula Zero just means that, I don't know anything about my opponents, but I still want to be extremely competent, and I still want to have a very high win rate against my opponents, right? And so distributionally robust online adaptation via offline population synthesis. There are a lot of words over there, and I'll explain each one as we go through this, right? So, so if you look at our, traditional, like this is a car trying to merge onto a highway over there, and it's trying to get this, the space between this truck and see if it can go through. And it's a pretty mundane situation for us, and we somehow, culturally, they're able to get through that, right? And but from an autonomous vehicles perspective, this is where it struggles in these kind of non-cooperative scenarios of like merging. Basically, it's trying to negotiate this merge it has to do that without delay or hesitation. But if it's too conservative, it won't merge and it'll just stand there, which is risky. And then if it's too aggressive, it could cause an accident as it goes through. And so how does it try to do that? But we want to look at not such a mundane situation, the most aggressive, where say we have Alonso and Vettel over here going extremely high speeds, extremely fast reaction times, extremely high cost vehicles, very dangerous racing at the bottom over here. And these two drivers are trying to guess what is the other driver trying to do. And their guessing is so kind of involuntary, it's just automatic. And they have to figure out a strategy where they are extremely close to each other and they don't want to crash, but they still want to sort of win this race, right? So we focus on racing because it provides us this extreme operational environment. But the issue here is that crashing is very expensive. These are multi-million-dollar vehicles. They're driving at over 200 kilometers per hour and very dangerous, right? Also, the sensors that are on board in an autonomous vehicle, like cameras, lidars, radars, IMUs, they don't sense, what is the opponent's intention, what is the opponent's strategy. They just sense very near-term things in terms of, what is the instantaneous behavior of the opponent, but not in terms of a behavioral model of the opponent, right? So we don't have sensors that actually can provide us that information. What we want to know is, what is this opponent's racing strategy overall and right now? And, and also, we operate in we can't just sort of mine how these opponents raced previously, say on the Austria track or on the Abu Dhabi track. Their strategies are secret, their vehicle components are secret. And so we operate in a very low data regime. We can't just mine how these competitions happened in the past, right? So we start with the basic robust reinforcement learning formulation, where we want to minimize, this expected cost of a set of actions over time. And so, but the problem is that, we have a lot of uncertainty both in how the opponent behaves and behaves around us, and how any action we make triggers the opponent to interact with us in some manner, right? And we are uncertain about that. And so essentially we have this set of PSA, which captures the state action transition probabilities, and going to model this, and parameterize this as a POMDP. And that's why we have this mini max formulation over here. If we knew exactly how the opponent's behavior would be, then we don't need this inner max. Essentially, we have this uncertainty ball around how this opponent is going to behave. And we want to take this factor in the formulation over here, right? So the overall idea is to, learn some useful parameterization for this uncertainty set P, and then, proceed as before with our RL formulation. So essentially, this is really trying to have some kind of a model of what is this predicted behavior of the opponent under every situation as we drive. And we want to parameterize that, right? Parameterize how much progress we are making and how close we're getting to the opponent. And so we want to do this. First, we do this in 2 steps. The first is the offline population synthesis. And essentially, we can't, sort of learn from how the opponent behaved previously. So we have to actually generate, our own kind of drivers using this approach called self-play, where we are iteratively generating a better driver that competes against all our previous drivers. And then it gets, then whoever wins that race, and then we keep getting more and more competent drivers in an offline manner. And we have to formulate what we mean by it's a good enough driver for this particular race. But the key aspect over here is that we don't just want, competent drivers that can race very fast, but we also want them to be very diverse, because if we just have one strategy, and then the opponent can guess us, right? So now essentially in this offline population synthesis, we generate a whole set of a variety of driving policies or drivers that are very competent, very diverse. And then we take those drivers to the race, essentially. But what we're trying to do is now we're trying to, in an online manner, we are trying to guess, of these policies that we have generated offline, what kind of combination or what is the nearest kind of driver that we've generated is the actual opponent, right? So we have this robust belief space for planning against this opponent, and we're trying to figure out, is this opponent like a mix of 3 or 4 of our offline generated policies? So then we can actually lower our uncertainty about this driver and then race more aggressively in and around that driver. So let's walk through this approach once more, right? So in the offline population synthesis, our goal is to generate a diverse set of competitive agents. And we do that by this policy parametrization for this uncertainty set. And essentially, as our car is driving around the track, our first thing is to have a set of trajectories that are generated that are good trajectories. And it's generating a set of goals and trajectories that go to these goals. And so essentially, we are continuously tuning this neural network to generate a good set of trajectories where we make the maximum progress. And then we have a goal evaluator over here that is really looking at, based on where the opponent is, what is the best trajectory, the lowest cost trajectory that we should take. So we both make maximum. So we make both maximum progress, and we are also safe from crashing into the opponent over here. So essentially, once we start with this offline process, what the offline process is doing under the hood is essentially now building a search algorithm for good policies. So we are generating now a set of drivers that we are now getting them to compete against each other. And we do this through this tiered optimization approach of tempered baths. Essentially, there are different levels of entropy as we're going through this. And I won't go into details of how this optimization works, but essentially, this is now generating agents, making them compete in simulation, updating the network, and then it is updating the optimization problem, where we basically end up with the most competent agents at the end of this, right? So we are basically iteratively generating new and new agents, letting them compete, pick the winner, and then generate more agents to see who can beat that winner. So, and the output of this system then essentially has a set of competent agents. Say we generate about 100 different agents that are driving policies that are very competent. That means they are neck to neck in terms of how fast they can drive around the lap, but they are diverse in terms of how they drive around and isolated in isolation. That means they have different paths. They don't just have a single racing line that they all converge to. And then they're also diverse in how they maneuver in and around opponents. That means they also have a variety of trajectories and approaches in which they are going to overtake an opponent.
So in the previous slide, where you're showing the trajectories, each trajectory here, the black lines essentially represent a different agent that you learn.
No, so this set of trajectories, say, would be what this particular agent has learned. So these are all essentially the viable trajectories, and then it is picking the lowest cost out of this trajectory. So this is one driving policy, like an agent with a given driving policy.
I see. And how do you generate this trajectory?
We
How do you decide this? How do you generate this diverse set of trajectories?
So that's exactly what is happening in this optimization step over here. That every time it's racing, each agent is using an approach to generate, say, a set of trajectories, and an agent that beats that would have a set of trajectories that are slightly different. And so they're continuously improving and out-competing each other. So by the end of this, what we have is a set of agents that have different kind of racing driving policies relative to each other. So relative to each other, they are just as competent, but they're also very diverse. Because as they have been going through, they are running a large series of races that are that are running through this system. I don't know who that is. Oh, okay. So let me hopefully explain that a little bit better in the coming slides, right? So essentially now we have generated an elite population of say drivers. Say we have about 20 different drivers or that have very different driving policies of how they're going to both do a lap in isolated laps, and also how they're going to navigate in and around certain around the best of the self-play system, right? So they can have a good enough win rate against each other or against all the other policies that we generated. And so now let's look at what we essentially do with this distributionally robust planning as we are. So first we basically draw a set of candidate goals, right? So essentially online, each agent maintains a belief vector, WT of the opponent's behavior pattern of these learned prototypes. Essentially, it's saying, well, it's trying to guess, this opponent is a mix of certain other agents that it has seen before. And essentially now we want to parameterize this ambiguity set P, as a ball around this nominal belief, WT. So essentially what this is doing is saying that I'm going to generate, according to my driving policy, a set of goals and the trajectories that get to these goals. Then I'm going to try to predict what this other agent is. And, and we'll come to that in the next slide. But essentially, based on that prediction, I'm going to then figure out of these trajectories that are generated, this is the minimum cost trajectory that will give me the maximum progress and also make sure I don't crash into that vehicle. So how do we actually predict what this opponent is doing, right? So you can think of that in this distributionally robust trajectory cost, where you can think of it in this belief space where, say, I have just 3 opponent models, right? In general, we have many more than that. But so if I pick, say, opponent model, this purple one over here, this is my ego vehicle, and in red, I have my opponent vehicle. And that opponent model guesses that this agent is going to go along this opponent model 1 trajectory. And then I find the minimum cost path for that trajectory. But it's making a guess. And then opponent model 2 predicts that this red agent is going to follow model 2's trajectory. And then opponent 3 has its own trajectory over here. And so each of these opponent models has their own guess as to what the other agent is going to do. But the other agent is not going to necessarily fit exactly one of the offline agents that we have. It's going to be some mixture of these offline agents. And there's also going to be some uncertainty as to that this is not a perfect fit. So essentially, we have this prediction in this belief space, but we don't represent it just as a point prediction. We also have an uncertainty ball around that. And that's what we mean by is distributionally robust, because we have this uncertainty that of this ambiguity set that we are taking into account over here. And That's what we are maximizing in terms of our expectation. So, so essentially now, as we start to drive around, we're making a consecutive series of guesses. Is it like opponent one? What kind of weighting is it? Of all our different candidate driving policies. So, for example, if there are 10 possible opponents that we are racing against, and 100 possible, motion planning goals that we are generating, we need to compute about 10,000 and 1,000 preceding horizon costs just for this, right? Usually we are, overtaking maybe one or two vehicles at a time, so it's not that high a cost over here. But what's happening now over time is that initially we have an equal weighting for all the policies that we generated offline. But as we continuously observe, and correct for, the weighting of how this opponent is driving, it starts to converge to a weighting of the different driving policies that we have here, and say this opponent is more of like policy 5, and then some other smaller weights of other policies that are here. And so this allows us over time, with just a few observations actually, to shrink our uncertainty set, and then we can drive more aggressively in and around this opponent. So, so let's first test our first hypothesis that was, on saying that, as we have higher robustness, that means the larger kind of, spacing that we want to keep, and the larger kind of more conservative behavior we want to have as we go down this to very conservative, we see that, the time to collision, which is essentially the, the opportunity of crashing or the likelihood of crashing into the other vehicle, that is, say, within 0.5 seconds, you're very close to the other vehicle, and we have a higher opportunity to crash with them, that goes down. So this means that the higher robustness we have means that there is an increase in the safety of the system, because our opportunity of crashing over here is getting lower. But this also means that, the higher robustness we have lower robustness as a threshold. We have almost a 60% win rate in this game. But the more robust we become and the more conservative we become, we actually have a lower win rate. And so that sort of says that, okay, well, we have, this downside of, of compromised win rate over here. So, but then when we have a win rate adaptive policy, which is basically saying that using this belief space, where we adaptively, are shrinking our our uncertainty ball around the agent by having consecutive observations, then we are able to regain the performance of aggressive strategies. And so that means that when we start racing, we don't know what driving policy the opponent has. And so we have a higher robustness. But then as we start to guess what the other agent is doing, we are able to drive more aggressively. And so we are able to now maintain a high robustness, but at the same time, still maintain our win rate throughout that, right? So you can eat the cake and have it too by having this adaptive approach over there. So, and then we evaluated this actually right outside Levine Hall over here between these two cars, just to see whether it actually works online, right? So these two are running Jetson Xaviers on board, and they're doing all of the computation of the online portion on board, right? So this car is observing the other car vehicle, and then it is trying to evaluate out of 20 possible driving policies, what is a combination of, I'm guessing, this other vehicle's driving policy. So as much for the theory that we do, we also want to see that it works. So obviously the issues with this sort of approach are that, well, what if the other agent, is out of distribution, right? They're not remotely like a combination of the driving policies we have generated through our self-play. Then normally what our system would do is it would just fall back to a very conservative strategy, because it just says, well, the uncertainty is too large, and then we are going to drive very safe again around that vehicle. And there could also be, more research along the directions of well, how do we, if we don't use these prototype behaviors, can there just be the online portion of the system that does not have to pick from these offline uh, prototype strategies? Uh, so that takes us to like the next problem on, how do we build the most efficient autonomous race car? And so here the question is that, if I have, and this is based on the tuner car paper that we had in ICRA on super optimization for autonomous racing. And what that essentially means is, I just switch to this over here, that I have many different knobs that are mechanical, that are planning based, that are perception based, and so on. Like these are just a few of the many knobs that I have to tune this vehicle for a particular racetrack, right? And to drive as fast as possible. And so how do I automatically tune this, but across multiple domains, right? And as I start to figure out how I tune it, the lap time can keep going lower and lower, and till I get to a vehicle that's drifting around this track. But how do I automatically do that? But I want to do that. I want to essentially have a reusable core of my autonomy stack, but the tracks and the vehicles can keep changing. And I want to be able to optimize for any new vehicle that comes along, right? So, but I want to be able to just optimize this stack over here. So that's what this tuner car approach did was, is minimizing, say, the lap time and taking, over 500 of these parameters that we have from mechanical to planning to control and mapping them to, a single scalar value. And essentially this approach, I'll just speak a little, I'll go through it a little faster. But this approach essentially is using like evolutionary algorithms or gradient-free optimization, because these are very non-convex cost functions over here. And we have a very high dimensional parametric space over here. So essentially by using gradient-free optimization approaches, these are like evolutionary algorithms. You can think of them as, largely greedy algorithms fall in these categories, is that they're continuously exploring and exploiting the search space of where you can find, higher the parameters with a lower cost, and they're evaluating them in simulation and eliminating a lot of candidates, and then exploring, and exploring the distributional shift in the candidates so far, and iteratively improving through this, right? So we ran this through many different gradient-free optimization algorithms, and compared to, say, just uniform or random search over here, we could compare how different gradient-free algorithms how efficiently they can search. We found that the CMAES, which was the most efficient algorithm, could actually has both diversity in the in searching, and also converts to the most efficient parametric set over here, where other algorithms weren't able to balance the explore exploit as well as CMES, where lower is actually better. So faster we can make a lap around. And so essentially this was a tool chain that could automatically tune the vehicle for a particular track. And then we wanted to see how well this tuning would work for the next track and the next track, and we could just do a very small incremental search for the following track after that. Another thing we looked at was, well, there are physical aspects, like cornering stiffness, center of gravity, and so on. There are decisions in terms of, your planning algorithm and tracking and control. So which ones affected the overall system? And we found that, the planning aspect, was much more dominant than the physical and the control aspects, as you might expect, but this actually tells you this very clearly, that it essentially, as we introduce noise in the planner or in each of these, the overall decline in the success rate of the system was what was basically related to planning much more than anything else over here. And then the nice part is that this actually then generates for us, both a racing line and an optimal race strategy. So it's basically saying, okay, input your parameters and outputs the best racing strategy to have for a single vehicle, right? And here you can see on the z-axis is essentially the slip angle. It's how much this vehicle is actually drifting along these curves over here, right? So, and here you can compare the dotted line is essentially like a model predictive contouring control. That's essentially a very efficient and safe planning strategy over here, race line, optimal race line strategy, versus the rainbow one over here is our strategy where this vehicle doesn't slow down much at the turns, but is essentially just drifting heavily along the turns and drifting along each of the turns as it goes through, right? So it had a much more aggressive strategy. And of course, the next step as we go through this is now to then run this on an actual vehicle. And so this is actually in Levine Hall, the entrance of Levine Hall. And so then we actually use this strategy and had the vehicle race around. And of course, it's going over a carpet, it's going over this grating at this end. So from smooth floor to rough floor. And so there is some sim to real gap, but it's a very small gap, as we can see from this generated thing. And this work was published in Europe and PMLR. And then the similar thing, many of you are in the class, they are doing this loop over here around this. And so this generated, a very high speed loop that is, comparable to the best of the second race that we had in the class. So then the next sort of directions for this kind of work are really focused on, bridging the sim to real gap and also looking at multi-agent systems and how do we actually do performance tuning, combining the first two thrusts for multi-agent scenarios where I want to balance the safety and performance, and I also want to optimize, my racing strategy when I am around other agents and when I'm not around other agents. Very briefly through the next two themes is really, there was this Indy Autonomous Challenge that was hosted in December last year and even in Jan, but where each of these vehicles I think are over $350,000 and they can reach peak speeds about 200 kilometers per hour. And they wanted to go directly and race them head to head. But in simulation, they found out that of the 16 teams, 12 of them crashed within the starting line over there. And they were like, okay, well, how can we have a head-to-head race? Because we suck even in simulation. We don't have good enough motion planning and control strategies to do safe overtaking. And so essentially, we focused on, well, how do we build a search engine that can efficiently search for crashes? And given, I'll just skip over these, but essentially we want to say, given a vehicle dynamical model and given a whole set of different planners and controllers, how do we actually now search along a given racetrack? And there are very different racing strategies to navigate around different curves of the track. How do we know how well we can operate in the presence of other agents? So essentially, this is very adversarial agent perturbation problem that says, okay, as I'm driving, I'm going to place an agent at this point, driving at this speed, or at this point, and this point. So we want to have a very efficient search. And we actually use RRT to place that agent in and around. And we kept iterating through that to see whether we can navigate in and around that agent based on where they were. Of course, if you place the agent right in front of us, that's not feasible. So we have to we have to have this agent that is sufficiently spaced out and see whether we can overtake that agent or at least not crash into that agent, right? So we're seeing whether we complete and overtake on this axis and whether and all these x's are basically showing, where we crash. And then when we get the result, we can display this as a set of, clustered crashes along each part. And then we essentially want to see, can we navigate, for example, this turn over here that has a lot of crashes, and how do we navigate that turn? We can also sort of see on a track, where do crashes most often happen, because we're really looking at all possible ways the other agent could be in and around us. And so we compare that across different planners and different controllers to find out, what's the best combination of planners and controllers, and how well do they perform, for different tracks over here. And so this just shows you, as this our purple agent is trying to overtake the other agent, and we're just iterating through many different driving scenarios, and it is essentially seeing where does it have success in overtaking and where does it fail along the track to be, rather than progressing along the track. And so this is essentially, we want to sort of see how we can efficiently search. Like, yeah, you can efficiently search, but the problem of efficiency is that if you're just starting out here and you keep crashing here, you never reach this part of the track because you're just crashing so much, you just can't survive along that path. So how do we actually, search for all of these turns, and then how do we feed that back into our racing strategy, right? So essentially, as we go forward, we want to look at, what are racing strategies for each of these components over here, and how do we automatically generate these strategies to lower the crash rate, right? And then there are, many different ways of trying to figure out, efficient ways for overtaking along each of these topological constraint environments. I'll skip this part on auto-generating. Maybe I'll just explain this high level. Is that so here we are really focused on AI co-designers for model-based design. And this is an ongoing project that will go on for 2 more years, at least. And so essentially the whole idea is that if I have many previous designs, say of drones, but we use drones for surveillance or for tracking transmission lines, and now we want to build a drone for, like, pursuit avoidance, and that they have to communicate with each other. So it's a different use case, different requirements. They have to be, say, more agile. So how can I mine these previous, drone designs? How can I break them down into their components, batteries, in their flight strategy, the planners, the controllers, and also in terms of their electrical, mechanical aspects, capture them in a knowledge graph. And then when I have a new sort of design that I have to make, how do I start to explore and search in this graph to come up with, partially completed new designs? And so essentially, we're doing this parametric and architectural exploration over here and comparing it with the seed designs, somewhat related to the early parts are related to tuner car, but now this goes well beyond, parametric searching. And so essentially, as we go through this kind of pipeline, the humans will say, okay, well, look, if you have a drone, it should have, say, like an even number of motors, and it should have, certain capabilities, certain flight lengths. So the human can input these sort of requirements over here. The human comes in and only, say, sort of when it generates a series of possible design, the human can eliminate a couple of them. Kind of like when Iron Man is trying to design a new system, and then Jarvis says, how about this, how about this? He says, no, not these two, let's look at this one. And so that's where the human is filtering these partially completed designs. And so essentially now, for the first part of this, we had a hackathon a few months ago where they gave us some seed designs where they had manually designed these different types of drone systems. And then we had to generate, new kinds of drones for certain different kind of benchmarks. So there were both, so there were designs that were based on these seed designs and then mining these seed designs. And then there were designs that just used, like, a variational autoencoder and reinforcement learning that came up with new designs from scratch. And you can see there are all sorts of weird and interesting designs. These are all feasible designs, right? And then there were a set of benchmarks. How far can the drone fly? How well can the drone track around a circle going counterclockwise? How fast can the drone do this loop? And then how high can the drone fly? And so then there were all these benchmarks, and then we had to just automatically generate and compete with all these other teams to see how well we could come up. So for how far a drone could fly, this was heavy powered drone and could fly the furthest. This second design was very weird because it's saying how well can this drone fly in the counterclockwise. So it figured out that the inner the inner motor does not have to do as much work. So it actually had an asymmetric design, and the drone was just flying counterclockwise. So I had to fly the other direction, it will have to rotate, and then it could only do that design, but it optimized just for the benchmark, right? So as we go forward with this, it's essentially, how do we replace this entire, like say if you're using MATLAB Simulink as a model-based design tool chain, how can we automate many of the intermediate steps? And there are sort of very concrete ways. So just tying it back, the reason we focus on racing is because this distinction between safety and the metrics for performance are very explicit. If I'm driving from Philly to Manhattan and I reach 5 minutes late, people are like, oh, okay, he's 5 minutes late, at least he's alive. They don't even say that, right? But in racing, if you're even 0.5 seconds slower, you're out of the top 10, right? So that's like, say goodbye to your racing career if you're too conservative. So you're also working with, we are driving at the limits of perception, planning, control, and so a lot of uncertainty. And so a lot of our algorithms are focused on just that, right? So just giving you a sampling of some of the research we've done so far. I'll just spend the next, 2-3 minutes on how you can get involved. There are a lot more slides. I'll share the slides. We obviously have F110, that is a course we are offering this semester. Many of you all are in this course or know about it. I'll skip over that. And there are many projects that we do with independent study on F110. And always reach out if you want to get involved in that. And then we have many races. We'll actually have the ICRA 2022 race this May over here, and it's a big race. There are dozens and dozens of teams that have registered both for in-person and virtual racing. And there are over 60 university partners that are involved with F110, both in the US and worldwide. And there are many other activities we have, like the opportunities and challenging with autonomous racing workshop that will be in ICRA. This is the second year we're offering this workshop. Last year there were over, I think, something like 700 people registered, and there were about 170 people, attending at any time in the workshop. One thing I want to introduce is on campus now we have this AutoWare Center of Excellence. And AutoWare is essentially the world's leading open source autonomous vehicle software stack, and that works on full scale vehicles. And it's a non-profit organization, and everything it does is open source. And essentially, the whole idea is that anything that moves will become autonomous. And so this is a software that will power not just vehicles and trucks, but also like in logistics, in warehouses, in cargo systems, any kind of system like that, right? So AutoWare is right in Pennovation. There is a space in one of the garages where AutoWare lab is, and so you can see that it's in this second last one over here. That person is standing in the image, and so that's where we are operating out of. And essentially, our goal for this lab over here is to build open AV software for these skateboard-like open EV platforms that are getting standardized. And that's a new way of manufacturing, any of these vehicle systems. Very different from how GM and Ford were doing it over the last 100 years. These skateboard-like platforms can just have any body on top. And essentially, we want to build the module that is the autonomous driving module for these platforms. They can be of any size, and it's a very flexible, standardized system. In this semester, in Feb, we had some experimental work on this autonomous to make this Lincoln MKZ autonomous. There was a workshop on the AutoWare stack, and just working on the drive-by-wire system. Many of these are RoboMaster students over here. as part of this. And there are many videos on how they actually were experimenting in the evening. And just this one weekend, they got the car to drive with a joystick control, right? So as you can see over here, and then the car is driving that manner in and around renovation. So with the LiDAR, GNSS, cameras, the entire stack is right there. So it's Schumann and Zihao, two second-year RoboMaster students, built LiDAR maps for innovation. And then they also built the semantic maps so that we can now navigate around innovation with the car. Autoware has over 60 industry partners. Content has over 60 university partners, and they all contribute software and sensors and so on to the Autoware Foundation. And there are lots of activities that we have within this. From my perspective, as faculty and working with students, this just gives us a lot of access to work on real stuff, and that's it. I think that's so. The other thing that we do is we have this Grand Prix. So come and attend it. Participate in it. And then we also have this workshop. There's a great lineup of invited speakers, and it was super interesting last year, and a lot of top speakers from Berkeley, Georgia Tech, MIT, Stanford, and this year we have a lot of people from Europe also. And then this is just one last project on autonomous go-karts. So we have a go-kart that we're participating in the EV Grand Prix. I shared these slides on the GRASP Slack also. So, but you can just see this is the track that we have to race on. It's a big challenge for us because we have to build this system from scratch, make it drive by wire, steer by wire, and autonomous, all in 3/4 of a semester. There's a really good team that's working super hard on this. They now work in innovation on Wednesdays and on Fridays, and you can join this team either now or after the summer. And so they're building this whole stack. They have this entire system, and each one of them have different modules they're working on. And we've got different sensors on board, and we're acquiring different sensors as we put them on board on the vehicle. And then as the track is there, they built like a smaller circuit in simulation. And so then this vehicle can now, even do some drifting along that. Essentially, this is all within the last, 3-4 weeks of this semester. This is all fresh material. This is actually our internal team update slides over here. And then you can see this vehicle, very tiny over here, but it's sort of at least doing some basic center line following along the track to get the simulator working. And and then there's, perception side of things of, phone detection and navigation along that. You can see there's a lot of room for improvement, and then it's improved over the last week, so, and now the team is in the process of building this. This is from last week and so on, right? So just to wrap up, there are lots of opportunities for everyone to get involved in autonomous racing, autonomous vehicle development, whether on the research side or just getting, hands-on experience. And that ends the talk. Thank you.
All right, thank you so much for presenting your work, Dr. Mangharam. Really thought it was interesting. We are a bit over time, but I do want to open it up for questions in case someone really had questions that they were itching to ask, both online and in person.